Alright, for this lesson we will be looking at power functions and characteristics of just polynomials in general. So let's first of all look at, well, what is a polynomial? So a polynomial is basically something you've been working with a lot of. Things like x squared plus 3x minus 4 is a polynomial. X to the fourth plus 3x cubed minus 7x plus 1. It doesn't have to contain each and every single power, and we should say y equals, things like that. But essentially anything with x to some exponent, you could have multiple x's in there to multiple different exponents. Those are what create polynomials. So we can write that out in general, and all this is saying is your x to some exponent n, and the thing in front is your coefficient. So your coefficient for that corresponding x, the next coefficient for the next corresponding x, so on and so forth, all the way to your constant at the end. So again, this could simply be something like 3x cubed minus 2x plus 1. And yeah, it's totally fine if you're missing exponents, like you don't have an x squared in there. That's okay. It doesn't have to every single thing. Just as long as you have x to some power, that is really what defines the polynomial. Okay, so a couple important things that we have with our polynomials is we have our leading coefficient. In this case, it would be an, which basically is the coefficient of x with the highest power. So if we're looking at 3x cubed minus 2x plus 1, the number 3 is the lead coefficient. And yeah, since we typically like to write polynomials from greatest to smallest exponent, or greatest to smallest degree, we're looking at essentially the thing that's out in front of the entire polynomial. The constant term is then the very last thing, the one that doesn't have an x on it. So sometimes we label it a naught, a0, a naught, and that's the constant term, so the thing without an x. Okay. And a polynomial function, well, it's just a function that is a polynomial. So basically all we did up there, but now it's just f of x equal to. All right, some important terminology to know with polynomials is what is the degree of a polynomial. Well, the degree of the polynomial is the value of the largest exponent. So the above is degree n, because then it's going down from n. So n minus 1 is smaller, all the way to squared to whatever it might be. So just the biggest exponent for x is the degree of that particular polynomial. So you're not adding up exponents if you have it written out in this form. Okay. And what we're going to be doing is we're going to try to figure out a little bit about the behavior of these polynomials. On the very first day, we saw that we're graphing cubic functions, and sometimes we can't use transformations to graph these cubic functions. So we do want to get a sense of what these functions, these polynomials, look like just in general. So when we refer to end behavior, we're going to look at the direction which a function is traveling from left to right, as in from the negative x values to the positive x values. So that's what we're going to look at, and we're going to see that through a number of examples. Okay. Just one other kind of function that we're going to look at is this thing called a power function. Really, it's just a specific type of polynomial. It's one where you only have essentially a single x. So it's of the form x to the n. So you're not adding or subtracting other values or powers of x, just the single x to the n. And you could have a coefficient in front of it as well too. So a to the times x to the n. is a power function. And what we're going to see is a lot of what we can do with a power function will apply to just polynomials in general. Okay, so we're skipping this. It's a video, but if you were in class, you would have done that. What we're going to see, though, is essentially with power functions, polynomials in general too, that as the degree increases, the graph, as it approaches the origin, so yeah, around the origin you'll see for the higher the degree gets, it gets flatter around, basically between -1 and 1. And then it gets steeper as you get outside -1 and 1. And why this is happening is essentially the higher the power or the degree, when you have really small numbers, so decimal numbers, something like 0.5 cubed, let's say, this is going to be 0.125, because a decimal multiplied by itself gets smaller. But then when you have a larger degree, you'll see that's even smaller than that. So that's kind of what's causing the flattening. It's just all numbers are really close to 0 then. But then as soon as you get to +1 or -1, that behavior changes. So 2 cubed is just going to be 8, but 2 to the power of 5 is going to be 32. So it increases a lot quicker when you're outside that -1 to 1 range. But within -1 to 1, the higher degree stays closer to 0. So there you have a little bit of difference between those degrees in that way. Some other key features that we're going to see is we should see there's going to be two kind of main types of graphs. There's going to be ones that are this curve that starts in the one quadrant and goes to the opposite quadrant. So things of odd degree. And we can kind of use x cubed as an example, but the ones above it will work as well. And then things of even degree. And the even degree ones are kind of that parabolic shape that we know from quadratics, essentially. So the domain of a cubic one or odd degree one is just going to be, well, everything. You can go plug in any number. And I'm going to use interval notation, the new notation we have. Same thing with our even degree ones. What gets different is when we get to our range. So the range for a cubic or any sort of odd degree one is just going to be, well, everything. You can get all the way into the negatives, you can get all the way into the positives. For an even degree, though, anything to the power of an even number is going to be positive or 0. So therefore our range is going to be anything bigger than 0. So we're going to use a square bracket because we reach the value of 0 and go all the way up to infinity. And the end behavior. So this is kind of a new thing we're talking about. So what happens at the end? So there's two different ways to describe it. I'm going to do it in both ways. One way to describe it is just to state, like as x goes to negative infinity, y goes to, so x going to negative infinity, we're looking as we go to the left. What's going on with our y values? Where we're going down with our y values. So with our y values, we're going down, so we're going towards negative infinity. Or, well, that's one end of the graph, the left end of the graph. I'll just kind of put that in, that was the left side. And the right side, well, the right side, as we go to the right, as we go towards positive infinity in terms of the x value, then our y value, well, I just made an arrow going upwards. So the y value will be positive infinity, so going to the right. So that's one way of describing the end behavior, is just say what happens to our y values as x goes to the left and as x goes to the right, as in towards negative infinity, towards positive infinity. Another way to indicate our end behavior is to use quadrants. So to use quadrants, how we can do that is we can state what quadrant are we beginning in from the left? So from left to right, where are we starting? And then what quadrant are we ending up in? And in this case, so we always go left to right, start, end. Doesn't matter what's happening in the middle. You could have the function going into all sorts of different quadrants up and down. All that matters is where do we start, as far left as we go, and where do we end, as far right as we can go. And in this case, we're in the top left quadrant, which is quadrant. Let's just remind ourselves of the quadrant numbers. Start in the top right and go in a circle counterclockwise 1, 2, 3, 4. So in this case, we would say the quadrant behavior or the end behavior using quadrants is quadrant 1, 2, quadrant, or sorry, not quadrant 1. We started in quadrant 2 there. We're quadrant 2 towards quadrant 1. That is the behavior there. So two different ways of describing end behavior. Both are totally fine to use, and you will need to be able to recognize both of them. Okay, so let's take a look at these. So we have a few polynomials. What's the degree? What's the leading coefficient? And then we can analyze a little bit more about end behavior based off of that. Okay, so for the degree, all you need to do is look at the biggest thing. You can probably go through this yourself, but just follow along with this too. So the degree is 3. The lead coefficient is 2. The degree is 5 in the next one. The lead coefficient is 3. And what we really care about is with those lead coefficients, this one's positive, this one's positive. And in the next one we have, just be careful. The degree is 7, so this one wasn't written in order of biggest to smallest degree, so that's where you have to be careful. And the leading coefficient is the one associated with that biggest exponent there. So the 2 is actually that. So the end behavior in this case is, well, we can see they're always starting in the bottom left and going up and to the right. So the end behavior of an odd, that's what we're dealing with there. Those are all 3, 5, 7 odd numbers. So an odd degree polynomial function with a positive lead coefficient will always go from quadrant, remember our quadrants, 1, 2, 3, 4. We'll always go from quadrant 3 to quadrant 1. All right. And yeah, for each of these parts, you can try it out yourself. It will hopefully be pretty easy just identifying degrees and lead coefficients. Okay, so we're going to look at things that have odd degree here, you're going to see. So, and we have a -2, so it's negative. That's what we're really looking at. Lead coefficient. Next one, have a 5 for the degree and a negative. So the negative sign is the real key thing. -1 is the lead coefficient. The next one, again, it's not written in the usual order, which is fine. We can still identify the degree, and we can still identify the lead coefficient, include the minus sign there. And so what you can see with these ones, while they're different shapes, the end behavior is still the same. They're all starting in that one quadrant in the top left and ending in the bottom right. So we can say the end behavior of an odd degree polynomial with a negative lead coefficient goes from quadrant, again I'm just labeling the quadrant numbers there, it goes from quadrant 2 to quadrant 4. Okay. Try this out yourself, and then I'll go through it right now, so don't hesitate to pause the video. Okay, so we've got degree 4, lead coefficient of 2, which is positive. We've got degree 8, lead coefficient of 1, which is positive. We've got degree 6, again, careful about the order of things there, with the lead coefficient of positive 3, which is positive. And so what we can see is with even, those are all even numbers there, in terms of the degree, with a positive lead coefficient, well, you're starting in quadrant 2 in this case, and going to quadrant 1. Again, we always go from left to right. So start on the left side, which means you're always going to be starting with quadrants 2 or 3, and you're going to the right, so you're always ending with quadrant 1 or 4. Okay, let's continue. So the degree here is going to be 8. Lead coefficient is -2. Negative being the key thing there. Degree in the next one is 4, with a lead coefficient of, -1, which is, again, negative is the key thing. And lastly, we have 6 as the degree, and a lead coefficient of, include that sign in front, -3. And so the end behavior is going to be of an even, so they're all even numbers, 8, 4, and 6 for the degrees. So even degree polynomial with a negative lead coefficient. We'll always go from let's see what we have here. So labeling the quadrant numbers, we're starting from left to right. We're going to start in quadrant 3 and go to quadrant 4. And so that's going to be the same for any even polynomial with a negative lead coefficient. And so summing all of that up, so there's a lot of different things there. So it'll take just a little bit of getting used to, so do spend some time going through the practice. But odd things you'll see always go from opposite corners. Even always go to quadrants beside each other. So odd degree with positive leading coefficient, that's like a regular cubic. So something like that I just drew down. And that goes from quadrant 3. Sometimes I like to write it just shorthand like that. So quadrant 3 to quadrant 1. Okay, I'm just going to do shorthand here on out. So odd degree with negative lead coefficient. So to remember these, again, sometimes just think of just either a basic cubic or quadratic as kind of your base examples. So a cubic has that kind of wiggle shape, but it's negative, so it's just pointing the opposite way now. So that's, looking at that, that's quadrant 2, it looks like, to quadrant 4. Even degree with positive, that's just a regular standard parabola like x squared. Well, if we take a look at x squared, that's quadrant 2 to quadrant 1. And if we have a negative in front, well, we're reflecting, so we're going downward. So that looks like it's quadrant 3 to quadrant 4. And that's how I remember these. So I'm not like memorizing all these different quadrant cases. I'm just remembering x cubed, negative x cubed, x squared, negative x squared, and then you can make out the different quadrants based off of that. Okay, so let's continue. So now let's do a little bit more analysis of a polynomial. So you'll see this polynomial is in factored form, but it could be in fully written out. And let's see, so we've got the sign of the leading coefficient. So if it's in factored form, the leading coefficient is just going to be what's in front there, so it's just positive. The degree of the polynomial. So this is where we have to be careful with factored form. We just need to add, and this is why we have to be careful, because if it's in standard form, what we had in all those previous examples, it was just the highest exponent. In factored form, you need to add the exponents of your factors. And by factors, I mean the brackets. So we just have 1 plus 1 plus 1. Let me write that a little bit better. Equals 3. So we have odd degree, positive lead coefficient, which means that we're going from quadrant 3 to quadrant 1. Or we can just see that in the picture itself. All right, number of maximum and minimum points. So do we have a maximum? Do we have a highest point? Well, we have this thing that looks like it's some sort of maximum, but we get higher in the graph on the right. And the graph keeps going up and up, so there is actually no maximum. Similarly with the minimum, we keep going down and down and down, so we have none. In comparison, though, we have these things called local maximums, local minimums. Sometimes we call them turning points, but a local maximum is a point that is basically the highest in the area, so that's a local max there. And at the bottom here is a local minimum. And so what we can see, those are also turning points because the graph is basically turning directions. It's going up and then going down, or it's going down and then up and going back up. So there's 2 of them in total. And if we take a look at the roots, that's what we would say is the x-intercepts. We have x equal to -2, 1, and 3. So we're just identifying things, just trying to get a better feel for these polynomial functions and some of their behaviors. And what we can see, what occurs at each root, the graph just goes through them. Okay. Interesting. We'll take a look at that and get a better sense of maybe some other things that could be happening. Okay. Let's do a similar thing. So we have a sign of leading coefficient. What's out in front? Well, it's just positive. The polynomial is, so adding the exponents of the factors, what you'll see now is you have a 2 on the x minus 3 and a 1 for the x minus 1 part. So it's 2 plus 1, which is equal to 3. End behavior then, and looking at the graph. So we need to be careful here. Because it's going down, it's still going to the left, still starts at quadrant 3. So it is still going to be quadrant 3 to quadrant 1. Even though, I mean, in the picture you can't see the part where it's reaching quadrant 3. So you do need to be careful, but that kind of matches up with what we'd expect from something that is degree 3 with a positive lead coefficient. All right, looking at maximums and minimums, does this graph reach a highest point? Well, no. Does it reach a lowest point? Well, no, because it keeps going down and up. So there's none there. But just like the previous one, do we have things that we'd call local maxes or local minimums? Well, we do. We have one here. That's a local maximum. It's above everything in the area, or it's a turning point you can think of as well. And we have a local minimum. So we have 2 of them. And then the roots. So in this case we have, as in the x-intercepts, x equal to 1 and x equal to 3, it looks like. All right, so what's happening here? We only have 2 roots this time. And we go through x equal to 1. But if we look at x equal to 3, it's a turning point. So that's a little different than what we had with the previous graph. And if you take a look at what's with our factored form there, x minus 3 squared, there's a little bit of a difference there. Okay. And that's where we're going to be seeing something a little bit different. It's this thing called the order of the roots. So the order of the root basically refers to how many times an x-intercept is repeated, if we're looking at it in factored form, let's say. So if we look at x minus 3 squared, x minus 1, x equal to 3 has order 2 because it's got that square on it, whereas x equal to 1 has order 1. And that is actually going to change the shape of the graph at the root, which is what we saw up above. If we take a look at that graph, at x equal to 3, it had a turning point. At x equal to 1, the graph just went through that x-intercept. Okay. So let's take a look at this last graph, and then we'll just summarize things, and we'll go from there. So for the graph, state the sign of the lead coefficient, the end behavior, and the roots. And what degree could the polynomial have? Okay, so let's just state the sign of the lead coefficient. So what we need to do is we need to look at the end behavior. We'll start with that, and then we can use that kind of working backwards. So the end behavior is quadrant 3 to quadrant 4. Quadrant 4. Since we're ending in quadrant 4, we're going down to the negatives. That's actually going to tell us that our lead coefficient, if we're going down to the negatives, our lead coefficient actually must be negative itself. Okay, continuing onwards, the roots and the order of each. So the roots, you have x equal to negative 2. You have x equal to 0. We'll get to the orders afterwards. And you have x equal to 2. All right, so for the orders of each, what you will get to get the orders is you just have to look at what is the shape of the graph around that root. If it just goes straight through, it's kind of going like just a straight line, let's say x equal to 2, well, that's just linear, which has degree 1, so order 1. We saw here, let's say at negative 2, it's got a turning point. That's kind of like the previous graph. So at negative 2, since it has a turning point, that's kind of like a parabola. If we think of a parabola like that. So a parabola has, well, degree 2, so it is order 2. And if we take a look at 0, well, 0 has kind of that cubic shape to it. So it's flattening at 0 and then continues onwards. That's actually going to tell us it's order 3. So there we have it. That's how we can look at a graph and determine the orders of those roots. All right. So summarizing, what we can say is for a degree n polynomial, whether it's degree 2, 3, 4, the number of x-intercepts could be the same. So you could have up to n. Whereas the number of local minimums and maximums, if you go back to those graphs, you'll see it's up to n minus 1. So it's up to 1 less. And we can actually make use of that in the above. So if we want to look at the possible degree of this one, you could have, based on the minimums and maximums, it would look like, well, 2 of them, so degree 3. Or if you look at the roots, if you add up the orders of the roots, that's like adding up the exponents in the factored form. At minimum, you could have, I should spell minimum, degree 6. All right. And let's continue. So use the characteristics of polynomial functions to describe and determine the following for each. So the least possible degree of the polynomial, the sign of the lead coefficient, the end behavior of the graph. So for now, what we can do is let's just take a look at the minimums and the maximums. There's 3 minimums and maximums. So by that, you could have degree 4. Because the minimums and maximums, there's always, at most you'd have 1 less than the degree. So we'd have to have at least degree 4 to have 3 minimums and maximums. The sign of the lead coefficient, basically we're looking at, is our graph as we go to the right going up to positive infinity or down to negative infinity? Since it's going up to positive infinity, it is a positive lead coefficient. And the end behavior, well, that's just directly seen. It's just quadrant 2 to quadrant 1. Okay. And the last example here, let's use the characteristics, the least possible degree of the polynomial. I mean, that's just directly from the equation. But let's go through the other parts. The sign of the leading coefficient, well, that again is the equation. Most importantly, though, so negative is the end behavior. How do we figure it out from the equation here? Well, we just have to look at the graph, or we just have to look at it as what's the lead coefficient and what's the degree. So odd with negative lead coefficient means it's like a cubic that's going in that direction, which means quadrant 2 to quadrant 4. All right, so there's definitely a lot to go through there. So really the key things to focus in on are those basic power functions, the cubic, the quadratic, x squared, x cubed. The end behaviors, those will be true for any odd degree or even degree polynomial. So being able to identify the degree of a polynomial, the sign of the lead coefficient is essential. And then there's some other little things like the number of local minimums and maximums and looking at the intercepts and what's happening with those in terms of the order of each of those intercepts. So a lot of little things in there, but hopefully each of the little things is actually fairly straightforward. You just need to do some practice to get used to it.